When I started out this lab, I anticipated it being relatively quick and straightforward, which it turned out not to be. I anticipated setting up 4 iOS VL2 nodes in GNS3 and then just deploying OSPF with Ansible. It turned out to be a little bit more complex than that. The iOS VL2 nodes started displaying instability when I issued the no switch port command. So I switched over to the iOS V images for the slab. These turned out to be a little too heavyweight for my machine. So I switched over to Cisco 3600 router images. And Ubuntu started complaining about outdated encryption algorithms with SSH. So I switched over to C7200 images, which also SSH complained about outdated encryption algorithms. So I ended up overriding the SSH encryption algorithms uh, and just going from there. So I settled on C3600 router images, and as you can see, I am setting them up in GNS3 now. Relatively simple setup. I'm using the cloud node as a uh, management backplane, so to speak. And yeah, so each uh, node is going to be connected to a layer 2 switch in GNS3, and the switch is going to be connected to the cloud node. As you can see, I'm setting that up now. I've already set up the links between the routers. And here comes the cloud node. And we're going to connect it to the tap0 interface. And starting the nodes right now. These nodes are located on another machine in my home lab. I found it more useful to offload the computing to that. As you can see in the upper right hand corner, the machines are at 10, 10, 10, 2. So we've got the node started. We're going to start assigning IP addresses. Conft, and each node has the management IP on interface F3/1. So there we are assigning the IP address 172.168.99.11 with a /24 subnet mask. And we're just going to use a username of admin, a privilege level of 15, and a password of admin. The enable secret is going to be admin, just same password there. Domain name of test.com. And we're going to explicitly assign a host name. And now we're going to generate the RSA key, 1024-bit key. Now we're going into the VTY lines and login local and transport input SSH. And we're doing the same thing for R2. Interface F3/1. IP address 172.168.99.12. 24-bit subnet mask. Username admin, privilege level of 15, password of admin again. It's going to be the same for every router. Enable secret of admin. Domain name of test.com. And hostname of R2, generating the RSA key, 1024-bit key, going into the VTY lines, transport input SSH, and doing the same thing for R3, signing 172.169.9.13, 24-bit subnet mask, username of admin, privilege level of 15, password of admin, enable secret of admin, domain name of test.com, host name is going to be R3, generating the RSA key, 1024-bit key, VTY lines, login local, and transport input SSH. Going into R4, assigning the IP address to the interface, 172.168.99.14, 24-bit subnet mask. Username, admin, privilege level of 15, password, admin. And enable secret of admin again. It's going to be the same on every router. Domain name, test.com. Hostname of R4. Generating the RSA key, 1024-bit key. Okay, going into the VTY lines. Login local, transport input, SSH. And now we're going to test SSH access. And there we have the error regarding the encryption algorithm. We are going to have to override that error. Okay, so we are now overriding the encryption algorithms for SSH. We're specifying the encryption algorithm specifically, and we're going to have to delete the SSH key. I went ahead and did that, and SSH appears to work. For R1, we're going to delete the key for R2 and SSH into R2. I'm going to say yes there, password, and SSH is good for R2. Deleting the key for R3 and SSHing into R3. Looking good. And R4. Deleting the key, SSH. We're looking good there. Okay, so now I'm going to walk through the Ansible files. This is a fairly straightforward lab, but it's a good example of how to structure network automation without turning the whole thing into a mess. The basic workflow consists of a pre-check, a base config, interface config, OSPF deployment, and then finally validation. So instead of logging into every router and building this manually, Ansible handles the repetitive part, and the project stays organized enough that you can actually follow it later. At a high level, the lab uses an ansible.cfg file, an inventory file, a few playbooks, host variable files, a group variable file, and a Jinja template for OSPF. Just the parts you'd expect if you want this to stay readable and not become a pile of random commands. The ansible.cfg file on the screen right now is minimal. It points to the inventory file, disables host key checking since this is a lab. It sets the output to a YAML file so the results are easier to read, and it uses explicit fact gathering. That makes sense here because these are network devices, and I am not treating them like Linux boxes. The inventory file defines 4 routers. I'm pulling up the inventory file now. R1 through R4, right here. Each has a management IP in the 172.16.99.0 with a 24-bit subnet mask range. That is what Ansible is connecting to. The inventory also defines the important connection settings for the whole iOS group. So network underscore CLI, Cisco iOS is the network OS, and then the login and enable credentials. Since this is a lab, I have made all the credentials, both usernames and passwords, admin. Okay, once you get past the inventory, you start to get into the variables. And there we go. The shared iOS variable file holds the common stuff. OSPF process ID, area, validation commands, and the baseline management settings, such as OSPF domain name, DNS, NTP, SSH key size, username, password, enable secret, and so on and so forth. That's going to create a common baseline for every router in the lab. After that, we have the router-specific variable files. These hold device-specific information. That is where each router gets its management interface, management IP, OSPF router ID, and the list of routed interfaces. And this is where the topology really lives. Each router has a list of interfaces with names, IP addresses, masks, descriptions, and whether the interface should be enabled. So instead of hard coding interface config directly into the playbook just reads structured data and pushes it. One thing that stands out in these files is the interface descriptions, saying stuff like was VLAN 10 or was VLAN 40. You can see these right here and right here and right here. Originally, this lab started off using routed interfaces, and then I changed router images and tried using VLAN interfaces, SVIs. That did not work well, and so I went back to routed interfaces. And so that is why the description says was VLAN 10, was VLAN 40, was VLAN 50, because this was originally in its second iteration using SVIs. So this shows the lab evolved instead of being built once and never touched again. So let's move on to the playbooks now. The first one we're looking at is precheck.yml. This is basically just a quick sanity check. It logs into the routers and runs show IP interface brief and show version. Doesn't do anything fancy. Just make sure that the devices are reachable and responding before the config is pushed. If it fails, there is no point pretending that the rest of the automation is fine. Now we're moving on to baseconfig.yml. This playbook bootstraps the routers with a basic management config. It sets the host name from the inventory name, pushes the domain name, login, logging, local admin account, enable secret, and SSH settings. One thing I like here is that it checks SSH status first with show IP SSH. missing or SSH is disabled. That's the kind of thing that makes the playbook less stupid, so to speak. It's not blindly trying to regenerate keys every run. It checks first and then acts if needed to. After that, it configures the console and the VTY lines, sets SSH only access on the VTYs, and disables DNS lookup so you don't get these annoying translating delays when you uh, when you typo something. You can see that right here. And then it optionally adds an NTP server. We are not using an NTP server in this particular lab, but there is a provision for it to be added later. So that playbook is basically the initial bootstrap layer that gets the routers into a usable state for remote management. Moving on, we're going to interface-config.yml. This is where the lab starts to reflect the actual topology. The first task asserts that the required variables are present. So it checks that management details exist, that routed interfaces are defined, and that there's actually something to configure. That's good because it fails early instead of letting you push a half-broken config and then figure it out later. After that, it configures the management interface using the values from the router-specific variable file. Then it loops through the routed interfaces and applies IP addressing directly to the physical ports. Again, this is one of the main advantages of doing it this way. The playbook doesn't need to know every interface on every router. It just loops through the data you defined per host and builds the config from that. Once it finishes, it runs a quick sanity check with show IP interface brief and show IP route connected. And then it prints the output. So right there in the playbook results, you can confirm whether the interfaces came up and whether the connected routes are present. Moving on, we are going to ospf-deploy.yml. This one uses a Jinja template called ospf-router.j2. The template builds the OSPF config using the shared process ID and area from the common variable file, plus the router-specific router ID and network statements from each router's variable file. So each router gets its own correct OSPF config without having to duplicate router commands in multiple places. The playbook renders the template into a fact, splits it into lines, strips out the blanks, and pushes it with iOS config. It's a clean pattern. Build the config from structured variables, render it, and then deploy it. The template also supports passive interfaces if they're defined, although in this lab the passive interface lists are empty since we do not have any end devices connected to the routers. Still, it's nice that the option is already there instead of having to add it to the template later. And moving on, we're going to ospf-validate.yml. This is the verification stage. It runs show IP OSPF neighbor, show IP route OSPF, and show IP protocol. Then it prints the output and also saves it locally, one file per router. This part matters because now the playbook isn't just pushing config. It's also collecting validation artifacts. So if something's wrong, you've already got the command output saved, and you don't have to go back and manually gather everything again. So overall, the flow of the lab is solid. You do a pre-check, To make sure the routers are reachable, you push the base config so management access is standardized. You configure the interfaces from host-specific data. You deploy OSPF from a template. Then you validate neighbors and routes and save the results. This is a real workflow. The other thing I like about this lab is that it's honest about what it is. It's not trying to be some giant automation framework. It's focused, it does a few things cleanly: inventory, shared variables, host-specific variables, template-driven routing config, and basic validation. Okay, so even as this sits now, I think this is a good lab. The structure makes sense and the intent is clear. It takes a 4-router topology and it makes it reproducible. Instead of rebuilding it by hand every time, I can run the playbooks in order and get consistent results. In this terminal session, I'm walking through a 5-step Ansible workflow to bring up OSPF across 4 Cisco routers. The first playbook is base config.yml, and this is basically the foundation layer before I touch routing. Right away, the first task checks SSH status on all 4 routers. You can see every router comes back OK, not changed. And the output shows SSH is already enabled, version 2.0, with RSA keys already present. That matters because the playbook has logic to generate keys only if they don't exist, and in this case it correctly skips that step. So that's already a good sign. The playbook is checking state first instead of just blasting config blindly. Then it sets host names from inventory names, and all those come back unchanged too, which tells me the inventory naming and the device naming are already aligned. After that, we get into the actual base management config. This is where Ansible starts reporting changed equals true on all 4 routers. You can see it pushing things like no IP domain lookup, IP domain name test.com, the enable secret, the local admin user, and SSH authentication retries. This is the basic management baseline. Nothing flashy, but it gives me a predictable starting point across the lab. A little further down, it configures the console line with an exec timeout. Then it configures the VTY lines for SSH only with login local. Transport input SSH and another timeout. Again, that hits all 4 routers cleanly. There's also a separate task disabling DNS lookup, which is a small thing, but if you've spent time on Cisco gear, you know it matters because it stops those annoying translating pauses when you mistype something. By the recap, every router shows OK equals 4, or OK equals 8, I'm sorry, changed equals 4, no failures, no unreachable devices. So base config is done cleanly across the board. Next up, we are doing interface config.yml, and this is where the actual routed underlay gets built. This play starts with a validation of required host variables, and every router passes. That's important because it means the playbook is not assuming the data is there. It checks first. Then it configures management routed interfaces on Fast Ethernet 3.1 for all 4 routers. I've already configured these interfaces before this, so this section is fairly simple. The changes are simple if they were implemented. Description management and no shutdown. The more interesting part comes right after that, where it configures the transit routed interfaces. and puts IP addresses directly on physical ports. This is a big part of what this lab is doing. You can actually see from the descriptions that these links used to be VLAN based, like transit was VLAN 10, was VLAN 20, was VLAN 30, and so on. So this is a clearly moving design that is moved from switched SVIs to routed physical interfaces. If you follow the updates, R1 gets 10.1.1.1 and 10.0. I'm sorry, R1 gets 10.0.1.1 on fast Ethernet 00, 10.0.4.1 on fast Ethernet 10, and 10.0.5.1 on fast Ethernet 3.0. R2 gets 10.0.1.2. R3 gets 10.0.4.2. And R4 gets 10.0.3.2, 10.0.2.2, and 10.0.5.2. So now you've got a 4 router topology with point-to-point slash 30-bit subnet masks built out as if the routing as it is a routing underlay. Then we come to the sanity check, and this is one of the most useful parts of this whole run. It prints show IP interface brief and routing table output so you can verify that the interfaces are actually up and that the connected interfaces exist before you ever touch OSPF. That's the right order. On R1, for example, you can see 10.0.1.1, 10.0.4.1, 10.0.5.1, plus the management IP of 172.168.99.11, all up and up. The routing table shows connected routes for those 30-bit subnet masks. Same idea on the other 3 routers. At this stage, there are only connected and local routes, which is exactly what I want to see. The underlay exists, but there is no dynamic routing protocol implemented yet. Now we are moving on to precheck.yml, and this is basically a lighter verification pass before the routing deployment. It runs show commands and confirms the interface state and the iOS version on each router. All 4 devices come back as Cisco 7200s, running iOS 15.3 parentheses 3xb12. Nothing changes here. It's all okay, no changed, no failures. So this is just confirming that the nodes are reachable, the interfaces are still up, and the devices are the platform I expect. After that, we are moving on to the OSPF deploy.yml, and this is the point where the actual routing protocol gets pushed. The first task builds OSPF config from a template, and I like that because it makes the playbook output readable. You can see the rendered config per router before it gets applied. R1 gets router ID 1.1.1.1 and network statements for 10.0.1.0 30-bit subnet mask and 10.0.4.0 30-bit subnet mask and 10.0.5.0 30-bit subnet mask. R2 gets router ID 2.2.2.2 and it has 2 transit links. R3 gets 3.3.3.3 and it has 2 links. R4 gets 4.4.4.4 and has 3 links. Then the play pushes that config and every router shows changed equals true. So the protocol process, router IDs, and network statements all land exactly where they should. The recap is clean, 1 change task per router with 0 failures. And now we're moving on to the last playbook, which is OSPF validate.yml. This is the proof stage. This one runs the OSPF validation commands and shows neighbor state, protocol details, and then saves the outputs locally into text files. On R1, you can see three neighbors: 4.4.4.4, 3.3.3.3, and 2.2.2.2. R4 also sees three neighbors. R2 and R3 each see 2, and this lines up with the physical topology that we have just built. Now, one detail worth calling out here is that the neighbor state is two-way DR other here, not full. Based on the output alone, I can say OSPF adjacencies are definitely forming and neighbor discovery is working. I cannot honestly say from this output alone that full route exchange is visible because the route table sections shown here don't actually display learned OSPF routes, and the validation output focuses more on neighbor and protocol states than end-to-end learned prefixes. So the safe read is this: the OSPF process is up, the router IDs are correct, the right networks are under OSPF, and the neighbors are being discovered on every expected link. The last task writes validation files locally for R1 through R4, which is nice because it gives you artifacts you can review later instead of losing everything in terminal scrollback. So overall, we have a clean run, base config succeeded, routed interfaces were built on physical ports, the pre-check confirmed the underlay was ready, OSPF was deployed from a template, and the validation step showed neighbor formation on every router with saved output files for follow-up. That's a solid automation work.